Well, hello. So this is just me going through the notes here, the PowerPoint that is, going over matter. So the first real chemistry unit here, after getting some science stuff done, right? Some basics of science, foundational work. So let's get to it. Trying to keep this video relatively short for you. Oops, that went way in the wrong direction. Let's try that again. Oh, I guess you get a little sneak peek of what we're about to do. Look at that. Okay. Yeah. Okay. So we have Unit 2 matter. And first thing you want to do is what is chemistry? And if you look at the dictionary, chemistry is the study of matter. And I mean, it's not that that's wrong, but it really doesn't tell you what it is. I mean, it's like saying it's the study of globes. You're like, what's a globe, right? Well, what's matter? I mean, matter is basically any substance you can think of, okay? Like wood, water, a table, you, air, anything. I mean, it's almost anything, okay? It has mass and it has volume. It's something that has stuff that makes it up. It has like, solidness to it. It doesn't have to be a solid, but it has, like I can't push through something. Even water like flows around things that you can't just like go through water. The water goes out of the way, right? And it has volume. It takes up space. Okay. The really only exceptions to this would be like energy. Okay. So like heat, right? Light, sound energy, right? These are things that, are not themselves matter. Okay. Sound requires matter. For sound to travel, it needs air or something else to transmit it. That's the way that wave works, right? But like light, heat, those are electromagnetic radiation. They don't need matter to transfer, okay? And they themselves are not matter, okay? However, what I want to stress to you is not just matter. You say, okay, yeah, matter is important. I also want to stress the idea that chemistry is really interested in electrons, okay? Like as we've learned more about matter, we've noticed that, hey, it's these electrons, that they appear to be the key to most questions in chemistry. Are there exceptions? Are there things involving the nucleus that are important? Are there things involving other features of the atom or of matter in general? Yeah, there are. But I mean, I don't think it's an exaggeration to say it's probably like 90% of chemistry is electrons and where they're at. Okay, so if any chemists want to jump in and say, actually, it's 87.3%, be my guest. But I don't think you're going to, I'd be surprised if anybody wants to argue it's not the majority of chemistry. So continuing. If we keep going forward here, we get into, well, what is matter? What are the properties of it? Said matter is anything that takes up space, anything that has substance to it. Okay, mass is kind of hard to describe because it's kind of like circular in the sense that you're like, it's stuff, and you go, well, what is stuff? It's mass. Basically, what I want for you guys to think about, and this maybe is a little too hard, but I hope it makes sense, is that mass is anything that can be affected by inertia. Okay, so like if I throw a baseball, the baseball has inertia, the baseball has momentum. If I try to catch the baseball in my hand, it'll push my hand back, right? If I walk into a wall, it hurts, it bangs into me. There's a transfer of force, there's a transfer of energy, and that hurts me because I have inertia and the wall has inertia. Mass is capable of doing that, whereas energy is not. If I blast a camera, what am I saying? If I blast a wall with light, the wall does not fall over, right? Light does not have inertia, as it were, okay? Now, if any theoretical physicists want to jump in the conversation, I'm sure there's a lot of them right now watching, maybe they're going to tell me, well, it's more complicated. But I think for this level, for high school, this is a decent way to think about it, perhaps, okay? But mass is basically substance, okay? Like you hold something in your hand, there's atoms that are there, and they don't just go through your hand. Okay, even sand falling through, it's atoms, well, molecules of it that are finding ways to fall through your hand. They don't just go through your hand, if it makes sense. Okay. All right, cool. And mass, as a consequence, has weight, meaning when you're on a planet like we're on Earth, gravity's pulling mass down, which means there's the force of weight pulling it down. Okay, so it can experience that. Light does not get affected by gravity directly, okay? I mean, if you're wondering what I mean by this, gravity bends space-time. That's relativity. And so light does bend because of gravity, but it's not because it's being pulled towards the mass, okay? So it's kind of complicated. You're probably going, what is he talking about? Don't worry about it. If what I'm saying makes no sense, ignore it. I'm just being a little technical here, okay? Don't worry about relativity. We're not going to do that in this class, okay? So cool. And I have this little side note down here, just saying that, I mean, if you want to be really technical, energy is basically, well, I should say matter is energy that's been condensed into, into matter. So energy condenses to form matter. Okay, that's what we currently believe. You've heard of Einstein's equation, E equals mc squared. Energy is mass times the speed of light squared. The idea here is that mass can be converted into energy, and vice versa. Okay, but again, you don't need it for this class. Okay, so like if you're taking notes right now and you're going, do I need that? Probably not. I'm just giving you that, just a little side piece of information. Okay, then volume is easier to understand. Volume is space. Volume is the canvas on which mass can be drawn, if that makes sense. Okay. Critically, it has to be a cubed unit. Okay. So if you're measuring volume, it's three-dimensional, right? It's length, its width, and its height, right? 3 dimensions. So if you have centimeters, it'd be centimeter times centimeter times centimeter. That's a cubic centimeter because it's cubed. There are 3 things being multiplied. They're all the same thing, so it's cubed. Cm times cm times cm, cubic centimeters. In chemistry, a lot of times we use what are called milliliters. A milliliter is 1,000th of a liter. Hopefully you remember back from the metric system. And thankfully for us, the metric system is logical. A milliliter, 1 milliliter, is the same thing as a cubic centimeter. So we often just say milliliters to make things easier, but it's a cubic centimeter. If you've ever seen a medical show, someone comes in the hospital, they say, give them 55 cc's of hydrazine. Cc's, cubic centimeter. Okay, so, but it has to be cubed. Okay, and it could be bigger. We could have cubic meters, which are much bigger, of course, than a cubic centimeter, or even things like a cubic kilometer, which is getting quite large. Okay, volume has to be conserved, which is a fancy way of saying if I put something in water, the water molecules get moved out of the way. Their volume gets displaced. So that's why if you get like in a bathtub, for example, the bath water rises because the volume of your body is displacing the volume of water. Okay, and that's actually quite useful because then if you wanted to measure the volume of something, you could just put it in water and measure how much the water rises, measure that increase in volume. Okay, if the shape is relatively normal, regular. Okay, regular is not quite the right word, but if it's a shape that's common, like for example a sphere or a cube or a rectangular prism or a cylinder, if the object you're measuring is close enough to one of those, I'm making that face because like you really shouldn't just assume something is a cylinder unless you know for a fact, right? But as long as it's close enough, you can probably get a good approximation of its volume with these equations you can see, courtesy of NASA. How nice of NASA. And for those math inclined students, just a way to see that math is used a lot in science, okay? But again, you could just take these shapes and put them in water and measure the displacement, okay? Probably a little bit quicker, probably a little bit more precise, as a matter of fact, more accurate, okay? Density then, so we're talking about mass, we're talking about volume, so I want to show you that these two things are related when it comes to matter. Okay, so depending on what you're measuring, whether it's water, whether it's gold, whether it's liquid silver, whether it's gaseous lead, whatever, the density of that object is a property of that object, something that is unique to that object. Okay, so density is how tightly packed are the atoms together in that substance, and also what is like the average weight of those molecules. So heavier elements like lead, for example, or osmium or tungsten are going to have higher density, partially because the atoms themselves are pretty heavy. They have a lot of protons and neutrons. Partially because they're pretty close together. Metals tend to keep their the distance, quote unquote, between atoms of metals. They tend to stick around a little bit closer. Okay, and if you're asking why, we'll get into that when we talk about the periodic table. Okay, but for right now, simple stuff. Density is mass divided by volume. Okay, and basically what this means is that if we were to put more stuff in a smaller space, it gets more dense, right? And if I take the same amount of stuff and put it in a bigger space, the density goes down, right? That's the consequence. That is the consequence of this equation, right? If the numerator gets bigger, density gets bigger. If the denominator gets bigger, then density gets lower. Okay, hopefully makes sense. All right, continuing. I clicked the wrong button. Silly Mr. Kara. Okay, so density. we look at this equation and we say, again, if it's bigger numerator, more dense, smaller denominator, more dense, and vice versa. Okay, this is a little visualization, right? This is just showing us a way to kind of picture this, right? So these cubes are 1 cubic meter, right? A meter, a meter, a meter, 3 meters times each other is a cubic meter, okay? And if I have 10 kilograms in this box, quote unquote, and 20 kilograms in this box, right, the density is going to be substantially higher, double as a matter of fact for the second one, okay? Hopefully that's making sense. This is just showing us that in the periodic table, right, we use that a lot in chemistry. If you look at these densities, right, you might notice a pattern, okay? So like the light gray is, less dense materials, and the darker green, I said gray, it should be green. The light green is less dense, the darker green is more dense. And you might notice, hey, the sides, right, the left and the right, are pretty low density, right? Helium is very, very, very low density. Hydrogen is insanely low density, right? Hydrogen is, as a matter of fact, this is one of the reasons it's so hard to contain hydrogen. Okay, it's very small and it very easily finds any little hole it can. Okay, so if you want to make a hydrogen car, if you're like, I want to make a hydrogen vehicle, that's a challenge as an engineer because hydrogen very easily can escape. And the fact that it's explosive, but that's a whole other conversation. So anyway, you see, hey, these are low density. Even metals like lithium and sodium, they're metals. They are metals. That's not an exaggeration. They float on water. Okay. You'll notice then we go towards the center and things begin to get denser. Okay, so you'll notice as we get in towards the middle, they get denser. And again, that's not a coincidence. This is not a, it just happens to be. The periodic table is a beautiful thing because there's basically no accidents in it. Everything has a reason. That's why chemistry is the best science. Sorry, biologists. Sorry, physicists. Chemistry is where it's at. All right, so you're looking here and going, wow, osmium and iridium are pretty hefty. Okay, and notice where they are. Pretty much right in the middle. Also, they're further down the periodic table, which also explains why they're so dense. Okay, so again, reasons. I don't want this to just be memorization. It's can I think of why? And maybe right now you can't say why, but that's okay. We'll get there. Okay. All right, continuing. Atomic structure. So density, we're done with that. Yay. Hopefully it's easy. Atomic structure, then I think we'll leave for the next video, so that way we can hopefully keep these videos relatively short. So see you in the next one.